Myself, Shivakumar, actually have 11 plus years of experience in custom analog layout. Okay, so I work for various companies and presently I'm working with one of the reputed product company. Today I'm going to give the demo on analog layout. Okay, what is the custom analog layout and what are the things you will be learning in the course? And I will give a brief like what is exactly VLSI, and then we'll make to know like what is analog layout and how it is different from your PD like physical design, and how important is the analog layout in the any IC design. Okay, this is the demo I'm going to give today. And agenda of this is I will be telling what is VLSI and where do we use our VLSI circuits. And then I will be telling like exact VLSI design flow, because you guys need to understand what is design flow before going to the analog layout. And we'll be like sharing you like topics which will be covered in the course. And finally, you'll have Q&A. Like if you have any questions, you can ask me. So I will answer it. Okay. Let's come to the topic. Like first thing is, what is VLSI? Okay, what is VLSI? VLSI is, as we know, as you guys have studied in the college and all, VLSI is very large scale integration. Okay, is a process of integrating or embedding hundreds of thousands of transistors on a single silicon semiconductor microchip. Okay, what do you mean by like embedding the thousands or millions of things? You guys should have remembered in your VLSI book, you first see the topic called Moore's law. Okay, what does that Moore's law tells? Moore's law basically tells that when you go like year by year, your transistors will increase. You mean to say when we take 1967 or 1970, your transistors like it was in hundreds. Then when you come into 80s, the transistors are increased to thousands or lakhs. Now it is millions and trillions of transistors. Okay, that's what the Moore's law tells. And that's where the all the VLSI like shrinking of the devices and all comes in the will follow the Moore's law. Okay, this is what the process is. Something like small transistors are integrated to make a big IC that depends upon the application of the IC. That's what the VLSI is mean. Okay, what is the use of VLSI? In our daily life, everywhere we use the VLSI applications. For example, when you are coming to your when you are coming to your sensors, when you use the modern cars, a lot of sensor. Before we used to have a big sensors. Nowadays it is very small chip. They will put it in your near that car in the front bonnet or something, so that it will be sensed easily. Before we need to put a big device near that, so that all this type of users will be there in the VLSI circuits. That's why VLSI has lot of scope in the industry. And also this is the evergreen thing. Like you need every time you will shrink it and you will make a device. Okay, this is what the VLSI and use of the VLSI. Okay, before going to the VLSI, like analog layout, I just wanted to like explain you about this chart or this PPT, like this design flow. This is something we call it as VLSI design flow. And why I had put this VLSI design flow is because you need to understand what is design flow before you guys going to the analog layout, because you have to know like what work you will be doing. Okay, because if you know what work you are doing, then you can do the good good type of projects or good type of execution mainly. Okay, that's what I will show, like where does that exactly this analog layout comes in your VLSI design flow, and later we'll see what that analog layout flow. Okay, first any design flow, any VLSI design flow. Okay, first of all, what is VLSI design flow? Basically, one has to start with the IC design. Okay, manufacturing a IC. IC means integrated circuit, or we in the simple terms or in our daily life terms we call it as a chip. Okay, the chip. We need to manufacture any chip. Okay, how does this chip manufacturing will start? The first thing, it will start with system specifications. Okay, what do you mean by system specification? For example, you will be seeing in your generation, as the generations is going day by day. First thing, in like 5 years back or 6 years back, we used to see that the mobile phones are very big in the sense the functionality of the mobile phones is less, means the operations are whatever options you get in the mobile phones are less because of area constraint. And then also used to charge for hours together to charge the 100% of battery. But when you come to the speed, when you load some video or you load some app, it used to rotate and take a lot of time. Okay, for now come to the nowadays generations or nowadays like whatever mobile phones we are seeing, where we see like your phone will be very fast and it will charge very quickly, and you have lot of options. Okay, for example, if you buy for 20K phone, you used to get very less options. Now if you buy same 20K phone, you will have lot of options. Okay, that's how the specification will start. See, every year, like for example, if you take a Intel processor, i4, i5, i6, how does it evolve? For example, the first they started with i5. Okay, after i5 release, they will take a feedback from all the customers in the market, means the end user, the people who are using in the market. They will take the feedback of everyone and they collect the information and they come up with something what is going wrong in i4 or i5, and then come with a new specification in the i6. That's what this is done by the system specification team. Okay, they will be having a separate team in any company, like MRD team, they call it market research development team. They will do a market research along the like everywhere, and they will take the feedback. Based on that, they will come with the specification. The specifications is mainly depend on three parameters. One is, let me take one new slide. Okay, this is, I will use it for writing. Okay, now let me take like system specification will start with three parameters. One is power. Okay, and one more thing is area, and other thing is speed. Based on this, the company will decide the parameters. Based on these parameters, they start the IC design. These are the main parameters. We call it as PAS, PAS. Some they call it as PSA, or these are the three parameters where any IC manufacturing will start. For example, now you take example as 8053 microcontroller. As you have seen in your colleges in the microcontroller labs, this 8051 microcontroller you need to design. This IC you need to design for some specifications, so for some power, some area, and some speed. Okay, this will get it from system specification team. Okay, once the system specification is done, then we have to design the architecture for that system specification. Okay, that is done by the architectural design team. What does this guys does? Now I need to start the 8053 microcontroller. Now what this architectural team does is they start collecting all the previous data regarding this 8053 microcontroller. Like, do I have any reused IPs, or I have any reused architecture I can use it, or I have any other blocks which I can use it for 8051 microcontroller. Because as you know, like manufacturing is IC is a big, like more amount of like money is invested here. It is not so simple. Okay, to design one IC, there will be a lot of millions of rupees will be invested. So they don't want to create a new design. So what they do, they start searching for the old design and they start implementing with same specifications for this 8051 microcontroller. If they don't feel like the design is not matching to whatever the specification we are getting here, then the people go for new design or new architectural. That is done by the architectural design. Okay, and architectural design also plans the like what all the things has to go, like how the things has to go and how the flow should go, and where and all I should stop the people, and where and all I need to check, and what all the deadlines they need to put it. Everything is done by the architectural design team. Okay, once this architectural team is done, like for example 8051, my architecture is ready. Okay, the architecture is ready means they have chosen that I will use 10 blocks totally in 8051, and I will use 5 reuse blocks, and I will design 5 new blocks. This type of architectural team would have decided. Now, when you come to the functional or a behavioral team, what does these guys do? Functional or a behavioral team, what they do is they start building the functionality for these blocks. Okay, now I have 5 blocks, 10 blocks total. Let me take 10 blocks like this. They build a functionality, like they will put these 10 blocks somewhere. If I have space, I will put it here, and they build a functionality. Functionality means like how many pins I need to get for this block, what is the output for this block, like this. This is what the functionality will be done. For example, if you take a mux, okay, mix multiplexer, or you take a decoder, okay, they will do a functionality for this. What does that functionality means? We'll be having one input per mux, okay, multiple inputs and one output. Like this, they will do the functionality of the mux. Okay, similar way for all the 10 blocks, they will do the functionality and they will have a data like functionality of that blocks. Like they will have the input outputs and how the input and output behave, and all will be done by this functionality team. Okay, this is what this functionality team will be done. Okay, this all the process which are happening at these three steps are there. This will be in very, very high level. Means it will be in very high level, like architectural design will be done in high level of your design. Okay, when the real design will start is from RTL design, lower level. Okay, from lower level, the real work of the any VLSI design will start, because everyone will know from here what is the work we are doing and what is the type of architecture we are designing. Okay, here in RTL design, once the functionality is ready, this RTL design people start writing the HDL code. HDL or VHDL code they will write. And now they are using the Verilog code. Okay, this is something they will be using VHDL or Verilog code, and they have something different process for RTL. Okay, these guys will write code for this write the code for my blocks functionality. For example, marks, or for example, I want to write a code for decoder, or I want to write a code for off rectifier or something other digital gates. They will write it and they will do their coding. Once the coding is done, next process is testing. Okay, any code which we do, we need to test it. Otherwise, we cannot blindly like pass that code to the other like next team. Okay, this was done by the functional verification and testing team. We can also call this team as DFT team, design for test team. Okay, this is one of the team which is coming here and testing the RTL design. Okay, once this RTL design is done, okay, once this RTL design and all your RTL is done, and then what we do is we synthesize the code. Like for example, for off-wave rectifier, we synthesize the code. Means we need to remember two terms, okay, synthesis and simulations. We need to understand the difference between synthesis and simulation. Synthesis is something we are generating some output. Simulation is one we are checking for whatever our output. Okay, checking the output with respect to input, we call it as simulations. Generating something from the input, we call it as synthesis. Once this functional verification means RTL is passed, then we do the synthesis of the RTL. Okay, synthesis of RTL is done, and the output of that synthesis will result in gate level netlist. Okay, gate level netlist, then we'll take it as an input and we do it as logical verification, or we can also call it as circuit design here. Once RTL is done, and we'll get the circuit design here. Okay, this complete process from top to bottom, from here to here, we call it as front end flow. Okay, this is the front end flow. This will be done in front end design. But this analog layout will comes in back end. Okay, we don't need to worry much about. If you are learning the back end, you don't need to worry much about this all the steps. But you need to know, like, because as a layout engineer, you need to know what's happening in your background. Because simply if you are doing a layout, anyone can do the layout and clear LVS DRCs. But what's happening in the background, if you learn, it will be good for you to do a good layouts. And also you will learn the more things in VLSI flow. Done. Now I'm done with circuit. Okay, this is how it will result. This will be the behavioral representation. I'm taking some off-wave rectifier as example, and this will be your gate level representation. And this is how your circuit is converted. Now your off-wave is converted into this type of circuit. Okay, this circuit have different types of gates like PMOS and MOS, and you'll have some other connections and current, something and all will be there. So that, yeah, that is what we are converting here. From logic to circuit, we are converting here. Done. Now, my front end flow is done. I have done with my circuit. Now, final step, if you see in the process, is fabrication. Okay, how the fabrication is done? The fabrication will be in layers. Whatever the fabrication it is going on the silicon will be on layers. For example, in the college, you have seen poly, metal one, or you may have seen the contact, or you have seen the oxide layer, something like that. So based on this, only it will go to the fabrication. If you take the MOSFET, like whatever the structure we have here, and take this MOSFET and put it in the fabrication, no, it's not allowed. We have a certain steps to follow in the fabrication. Okay, based on that, now this logic we need to convert into a layer form. That's what we are doing it in the backend process. Whatever circuit we are having, that we are converting into layer format in the backend process. Okay, this backend process till year, from year to year, we call it as backend process. Till physical verification and sign off, we call it as backend. Okay, in the backend, whatever we are doing, whatever the backend year we are having, we can also call it as PD, physical design. Okay, we call it as a physical design. Okay, see, how can you understand this complete physical design in, now means physical design means the planning of your chip at the top level. You can visualize simply in the terms of like, how do you build your house? Okay, how do you build your house? First thing, whatever the circuit diagram you are getting from the designer, you think that it is a plan approval, like a plan approval from the engineer. Now you got a plan approval from the engineer, you need to start your building. Okay, first, what you do it? First we do like, first we start with our area. Correct? We decide in how much area I need to build my house. For example, 30-40 or 60-40. Similar way, first we need to decide how much area I need to require for this block or this IC to build it. Okay, that is the first step we start with. Okay, next step, once our area is fixed, then what we do is we do partitioning. Partitioning means we start building, we do partition like this. Like how much area I should reserve for my how much area I need to reserve for my living room, how much area I need to reserve for my washroom, how much area for my dining hall. Similarly, we do the partition. That is what we do in the chip also. Like we do the partition. And again, we do the chip planning. See, what does the chip planning again comes? Like how much, if I am having the block, if I am having a bedroom here, like or living room here, how this connection should be, is it proper or not, interconnects, and all will be done in the chip planning. Next, we come to the placement. Placement is like how my electrical connection should go, how my sanitation work should do. All this we'll do it in placement, right? Similar way in the chip also, we plan for the routings, like how the routing should be there from block to block, and where the block should sit. For example, I have a block here, and I have more like here I have some noisy block sitting here. If I put one block near to noisy, what will happen to this block? Okay, if there is something noise is introduced into this, so I need to push this block away like this type of things. Based on this, we do the placement. And then once the placement is done, we do the signal routing. This we call it as signal routing. See, once your all the rooms are done, all the partition is done, we need to integrate all together. That is done in the signal routing process. Okay, this what we call partitioning, chip planning, placement, signal routing. It will come in PNR. We call it as place and route. Okay, this is one of the domain of PD, place and route. Okay, in the place and route, we do partitioning, chip planning, placement, and signal routing. Then we have something called physical layout and verification and sign off. Now, whatever circuit we got, we have done our layout. Our physical layout is done. Now, we need to verify you have done proper physical layout or not. Okay.
Hello.
Yeah. Is someone have anything? Okay, fine. Yeah. So once your physical layout is done, we have something called physical verification and sign off. Here, what we do is our layout is ready now. Our layout is ready. So what we are doing, we are verifying our layout with respect to our verification. Means with respect to our circuit, is it correct or not? Then it is correct. Then then we'll send for the fabrication. Okay, here we verify like basic flow called LVS and DRC. Okay, what is this LVS and DRCs? I can explain you in coming slide. Okay, I can tell you here. Schematic LVS means layout versus schematic. Here we are verifying whatever the schematic we have, like whatever circuit diagram we have here with respect to the layout. Okay, is my connections are correct? All the devices are placed properly or not? We will be checking in the LVS. DRC is something called design rule check. Here we need to, since we are dealing with our layers, we need to maintain some design rule checks which are coming from design rule deck. So that will be checked in the DRC. Okay, these are the two things we will be checking, DRC and LVS, and there will be a lot of other flows which are checked here, but main things are DRC and LVS. Once your physical layout is ready, then we go for the fabrication, and then we do the packaging and testing, and then we release the IP. We release IC or our IP. This is complete backend till the physical verification and sign out. This is the other process which will be coming in the next steps after your layout is ready. Means once your chip is ready, they will do fabrication, then they will do packaging and testing. Packaging and testing is similar like we see our IC and we have the black colors and pins are getting out with the silver lines, right? That all will be done in the packaging and testing process. And finally, the IC will be reduced. IC will be released to the market on time. Okay, that again depends upon the time in which we release the IC to the market. Now, this is complete VLSI design flow from starting of the chip to the complete release of the chip. So whatever chip is coming out, it has to meet the system specification we got from the system specification team. Okay, this is the physical design flow. But now you need to understand what is the custom analog. First of all, we need to understand what is the custom analog. Now you know about how you design the IC, like one full chip, how you design, you have come to know from front end to back end, from RTL to back end still fabrication. Okay. Now your chip is ready. Now chip is ready. When you have a back end process, like you have a blocks like this in 8053 microcontroller, we see there are the blocks. Okay. These blocks is what we will be designing. Analog custom layout engineers are the engineers who design the, who put the layouts for IPs. What do you mean by IP? Intellectual IP is like intellectual property. We can give example like IPs like LDO. You guys would have heard about ADC, analog to digital converter, and DAC, digital to analog converter, and you will have something called PLL, phase locked loop, and something called phase locked loop, and you will be having rectifiers. Okay, and you will be having oscillators. These are all, we call it as IP. Okay, this we call it as IP. So we will be designing these IPs. Okay, so the people will take this IP and put it on chip level, and they do whatever I have explained here, right? They will do it and they will release the chip. But what is the work of our thing? We are designing this IP. Okay, we are designing this IP, and PD people will be utilizing our blocks and they will integrating it and they are releasing it. So we are analog layout engineers who are designing the IPs. Okay, in the analog also you have two teams. One is design team and one more is layout team. Okay, design and layout. Layout people, design people will design the circuit. Layout people will put the layout and will deliver the IPs to the PD team. So PD team will integrate at the top level and they follow all the steps whatever required for the chip, and they will release the IP like IC to the market. So this is the work we'll be going to do. Like we'll be doing a layout for IPs. Okay, layout for the IPs. So this is what the basic overview of what work you will be doing. Okay, maybe the schedule I have planned is like I will be like teaching starting with overview of design flow. Maybe this will go a little bit deeper into it, and then essentials of some Unix or Linux commands. Like we need to know few Linux and Unix commands, because all the tool which we use here, like Virtuoso and all, will be run on Linux environment, not on Windows environment. It doesn't support on Windows environment. So all the tools will be run on Linux environment. So we need to run on Linux. Okay, so we need to know few basic commands of Linux, which is very, very useful. And also it's required for your debug when you go to the industry for working. Okay, that's what I will be like, we will be planning to teach you about the essentials of Unix and Linux. Then we will be studying about basic semiconductor basics, like what is conductor, what is inductor, like what is conductor, what is semiconductor, and what is insulators, and intrinsic and extrinsic semiconductor. These are all the basic concepts you should know. Okay, to understand the MOSFET, or if you wanted to do a layout, you need to understand all these things. Otherwise, it's very, very difficult for you to do a good layout. Okay, there are difference between doing a good layout and difference between doing a layout. Layout anyone can do. There is nothing like this person cannot do or like that. But end quality of the layout matters a lot. Okay, layout should be quality. Then only whatever IC will come out will be very quality and it will be meeting our expectations. That's why we need to learn about our semiconductor basics, and also you need to learn about electronic basics also, like Ohm's law, Kirchhoff law, and basics of circuit understanding. Okay, because we will be like whatever the quality of the layout will be in the terms of resistors and capacitors. So before you handle the MOSFETs in the MOSFET, you need to know about Ohm's law, and also you need to know about the capacitors and resistors. This will be covering in one session separately in semiconductor basics. And one more thing we will be covering is CMOS and FinFET basics. Okay, CMOS and FinFET basics. But we'll see like FinFET, if we'll see about FinFET. That see, there are something like you have BJT. Again, after BJT, we overcome and we came with a new plan of CMOS. After CMOS, now there is a FinFET. Now in the industry, it is running is ribbon fed. No, like this, the channel length will reduce, and like that, the new technologies will evolve. Okay, we'll study about MOSFET basics, operations, and few simple circuits and second order effects, and we'll study the complete detailed fabrication process. As a layout engineer, you need to know the fabrication. Otherwise, it's very, very difficult. You need to know each and every layer, how the MOSFET is fabricated, like how the NMOS is fabricated, how the PMOS is fabricated. What is NMOS and PMOS? We will be learning in semiconductor basics. Okay. Once this is done, these are all the basic things. Once we'll be covering in few sessions. Once all these sessions are done, then we'll go for layout tool. Okay. Layout tool. First, you need to understand the layout editor tool. Then you need to understand schematic symbols and parameters, like what is schematic and what is layout, what is symbol. There are a lot of things. And how do you manage the libraries and commands for layout editing and DRC verification, antenna effect, latch up migration, electro migration, IR drops. These are the few concepts which comes in the analog layout. Okay, there are two types. One is digital layout, another is analog layout. Analog layout and digital layout. Okay. In analog, we need to follow a lot of constraints because it is analog. Okay. Digital, very less. Digital, you can predict the signal behavioral. But analog, you cannot predict the signal behavioral. Every time it changes its activity. Like every change, it changes its properties. That's why we need to do very carefully the analog layout, but digital layout, somehow you can do it. But analog layout, you need to maintain a lot of constraints like electro migration, latch up, antenna, this and all things you need to take care. And few more concepts will come, shielding, some others concept. We will be covering that complete concepts in your training sessions. Okay. And then this is the something, and later we'll have something called advanced layout concepts. We will be checking here what is the failure mechanisms and noises and couplings and full chip construction. And we'll be explaining that how this IC will be integrated in the full chip. And physical verification, same, like we need to run verification, that is LVS, ERC, antenna checks, and latch up. We'll have some restrictions for the tool. If there is availability, we can do the latch up also. And then we do the hands-on, like hands-on project. Okay, first thing we'll be doing all digital circuit. We'll complete all the digital circuits. For example, okay, we'll be completing all the digital circuits, like your from your inverter to your XOR gate. Then we'll be completing from your D latch to your JK flip-flops. Once that is done, then we come from the analog circuits, where we'll be having some current mirror input pairs, and then we'll do some LDO type of blocks. If we have a good schematic of ADC, we can design the ADC also in the layout. Okay. These all the concepts are covered in detail. We'll be studying in the courses, and these are all the projects. What I am planning to cover it. Like we can have a standard cell digital layouts of digital gates, level shifter, Smith trigger, single stage op amp, 4-bit flash ADC, and then 4-bit DAC, band gap reference with startup circuit, and we can have low dropout voltage regulator circuit. These are all the some of the projects I'm planning to cover. This will be your floor planning, schematic, and layout. Okay, you need to do a schematic as well as the layout. This is the something overview I have planned for this session. So if you guys have any questions, you can ask me.
Guys, you can unmute and answer questions.
Yes.
Yeah.
Sir, what are the tools we're gonna use to
What are the
tools? What are the
tools?
tools?
Yeah, tools we use is okay, Virtuoso. That again will be like wrapped into Cadence. And then for verification purpose, we do use Ashura, and we have Diva LVS, and we can also integrate Caliber. All three we can integrate. There is no limitation. But whatever I have, what plan I have is 45 and 90 nanometer. That is the PDKs available in the market. Yeah, now for you will work on 45 and 90 nanometer with Ashura tool and Diva also, and also we can integrate Caliber also. But Virtuoso is common. This verification tools we can integrate. That's not a big deal. We can do that one. If you
Crack
know,
version is
yeah.
available, sir.
Hello.
So crack version is available for practice or not for the all
Yes.
of these tools?
Yes, all the crack versions are available. I think Praveen, right? Praveen. Okay. Yeah, crack versions are available. No issues. We can integrate. See, I have a experience in IP like designing a layout, and I also have a experience in CAD. CAD means the person who works on tool. Okay, so if you give me some tool, you tell me to edit something in the tool, I can do it. That is the experience I have. 3 to 4 years of experience I have in CAD. So we can integrate easily the tools also. Like if we get a crack version, we can integrate and do it. But Virtuoso will be common. We cannot do anything for the Virtuoso. Anything else?
So total duration of this complete training, how long it will take?
It will be 3 to 4 months. Again, it depends upon your interest. 3 to 4 months is the training period. Yeah, maximum 4 months.
Okay. Sir, when will you start this course with full-fledged?
We will discuss about that on the
Yeah.
Anyone have any question regarding technical questions?
Yeah, technical questions you can ask me. I can answer you.
Okay, sir, could you please explain that clock tree synthesis that
Okay.
you have shown in the globe?
Okay, sure. Yeah. Maybe because why I skipped this because it doesn't relate to layout. That's why I skipped. If you want, I can
Yes,
explain.
that clock tree synthesis and timing closure.
Yes. Okay. See what happens in the PD physical design flow will be having 3 domains usually. See, PD is physical design, but again it is divided into 3. One is PNR, that is place and route. The other team is we call it as physical verification team, PV team, and one more team we call it as synthesis team. Okay. PNR we covered it. Partition, chip planning, placement, signal routing. And physical layout is ready. And physical verification, we have covered it. These guys will do the physical verification. And there will be one team called physical synthesis team. They call it as synthesis team. What they do is they work on clock tree synthesis and time enclosure. Okay. What do you mean by clock tree synthesis? For example, if you have a block like IC and lot of IPs are sitting like this. And you should remember that, or if you guys have some knowledge on clock, the clock is the one which triggers the block. Any block which need a triggering, it is done by the clock block. So we design one clock. Now this is the clock signal. It is going for each block. Now what happened? We need to analyze these signals. Okay, what is the delay in these signals which is reaching at a time, and what is the delay for reaching this signal? I am given only one clock, but there will be multiple clocks for the multiple blocks. So that is done by this clock tree synthesis team. What they do is they will synthesize the clock. Okay, again, synthesis means they will be generating the output from the clock, and they will be analyzing what is the things happening, the block reaching time. If they found something weird, again they will tell the PD guys to alter the routings. Okay, again, if they see resistance capacitance more, it will obviously impact your delay. That's why we do the clock tree synthesis. People will synthesize the clock which is reaching to the block. Now, timing closure is something we call it as PVT. Okay, process, voltage, and temperature. For any chip to operate, these 3 parameters is very, very important. Process is one
the technology you are working on. And voltage is the voltage where this IC will be operating. For example, this IC from outside you will get 230 volts, but each block will have different types of voltage requirement. Like this block need 5 volt, this block required 3 volt, this block required 2 volt. Okay, this voltage. And T is temperature. Temperature means what temperature this IC is flexible, like 110 degree. If it go for 130 degree, this IC will damage. This type of things, they will have this area, PVT, process variation and temperature. They will have some corner cases, like again, that is a different topic, like different corners they will have, different corner. I don't remember that corners. And based on this, they will close on the blocks. Like for this PVT, what is the things happening for this block? And for that other PVT, what is happening for this block? This all will be done in the timing closure. So this will be handled in synthesis. PNR is the one who will be doing the layout. PV is the verification. Okay, this is what synthesis. In the synthesis, we will be coming this clock tree synthesis and timing closure.
Got it.
So should we end the meeting? Anyone have any doubt or other doubt? Okay, then sure. I guess we can end the session.
Okay,
Okay,
sure.
thank
Thank
you
you.